get started. So let me review what we are talking about here. So we're talking about inflation here, right? Like it's what is a very in the very early universe, right? And then after that, there's a Big Bang's fireball was there, right? And the universe keep expanding. So okay, after inflation finishes, you remember the potential energy is gonna come to the minimum, and then this potential energy is going to be transformed to matter and then radiation in the universe, which were written here. And then so after inflation, this Big Bang's fireball starts, right? And then this universe keep expanding. It's not it's not inflation anymore, but then it's slowly still expanding. It's part of the Big Bang. And then now there's a matter and then energy in the universe. And then we also did the Big Bang, right? So we have electrons and then protons, and then there's an electron and there's some interaction, right? What was a very important concept to form the elements in the early universe? Do you remember we discussed? Protons, the neutrons, the ratio was, what happened? When protons and neutrons ratio was fixed, do you remember? Big Bang nuclear synthesis theory.
I remember you talked about this, but I can't remember the ratio.
No, I'm not asking. Freeze out. Do you remember freeze out? Mm-hmm. Freeze out. So when the temperature goes down, then these becomes, elements are created in the Big Bang, right? So that's happening here, like first 3 minutes of the universe. And then so the universe keeps expanding, right? Then when the temperature becomes low enough, these electrons and then protons, they get combined and then create a hydrogen atom like this. So before, when temperature is high enough, it was ionized, right? They were ionized. But then now, it's combined to be a hydrogen atom, right? By the way, who are presenting today? Is it Wen, right?
Wen and Puto, we are.
Oh, okay, you guys are here. Okay, that's good. Okay, very good. I was worried that maybe speaker is not here. Okay, then when the universe become neutral, when the hydrogen ions becomes hydrogen atom combined, then the photon can go through the universe. Because here, before this is called recombination, the photons are there because high temperature, but then it bumps into electron, and then you have a Thomson scattering, like photon bump into electron, it's scattered, right? So photon cannot go straight. It's bumping into electron and then change direction, scattered. So it's not, universe was not transparent. Photon cannot go through. But after the recombination, there's no more free electrons, right? Electrons are combined with protons to make a hydrogen atom. So they can go straight. Right. And then this is what we observe as cosmic microwave background now. So this is a moment at redshift 1000 where cosmic microwave background is emitted to us. We cannot see here because photon cannot go straight, but we can see what's there. So when I show you Planck or Colby or WMAP, CMB map, that is a map from this moment. The temperature fluctuation of cosmic microwave background, we are observing fluctuation at this time. This is sometimes called last scattering surface. Okay. And then, then photon comes here, but then somehow, if you know that the universe today is also ionized. If you look at the night sky now, if you go to space, you look at the space, you go to space and then it's ionized, right? You've been to space, right, before, and then it was ionized, right? Right?
Yes, yes.
Yeah, you have not been to space, but then we know it's ionized. So this neutral hydrogen was reionized by the first galaxies and stars from the UV radiation from star formation or black hole, and then this is called the reionization. And that's why the current universe is also ionized towards us. So this is a very brief history of the early universe. Please have this picture, okay? This is a side story, but we call this CMB emitting large scattering surface as recombination when protons and electrons combine to make hydrogen atom. But this is not This is the first time they are combined because they are ionized at the beginning. They never get combined. This is the first time, but conventionally we just call it recombination. And then this, after neutral hydrogen is ionized by galaxies and black holes, we call it reionization. And we call it means second time, right? But this is the first time they were ionized. Because they are ionized here, but this is not ionized. This is from the beginning, it was like that. So from neutral to ionized, this is the first time. So both of these are first time, recombination and reionization, but we call it reionization and recombination. Anyway, that's a little side story, but then today we're going to analyze this fluctuation of the cosmic microwave background. And then, please, remember that this fluctuation is fluctuation on this surface. Okay? Yes, question?
Yeah, like the cosmic CMB.
Yes.
We see, like you're saying it happens at this time.
Yeah.
But that it means one day we will not observe any more CMB.
No. We observe. Yeah, that's a very good question, because universe is filled with this.
It's everywhere.
Yeah. Okay. So this looks like one dimension, right? From here to here, right? But then it's actually, this is a timeline, and our Earth, we are here in the middle of here, and this is just a timeline. So everywhere was there, and then the whole universe is filled with this radiation. It's coming from every part of the universe. So we continue observing it. The temperature goes down with this, right? With the expansion of the universe, temperature is going to slowly go down. But we keep observing this because it's everywhere. Like, I don't know, how do you... Like, okay, on a sunny day like this, if you go outside today, temperature is high, right? It's hot, right? And then you move around or stay around, it's still hot, right? That's because this heat is everywhere. The CMB is like that. CMB is heat, so it's coming towards us all the time. Okay, then let's look at the fluctuation here and analyze today. Okay. All right, so here. So, as I briefly mentioned, at the time of the Big Bang, photons are scattered by electrons from Thomson and Coulomb scattering. Okay? So with this scattering, this Big Bang, at the time of that time, universe was photon baryon fluid. You know, photons and baryons are mixed. Photons and electrons, protons are mixed. And then, if it's a fluid, then there's a gravitational potential, right? So we learned from inflation, there are some higher temperature region, lower temperature region, or some larger gravitational potential and then less gravitational potential, right? So there's a gravity. Say a little bit hotter region have a little bit larger gravitational potential. And then photons also have pressure, right? In a hot region has more photon pressure, right? You feel that if say this region is a little bit hotter, then you feel a radiation, right? There's a radiation pressure. So what happens if someone is pulling and then someone has a pressure, then there's oscillations. So, you know, it's a pulled and then push back, pulled and push back, there will be oscillation. Say, for example, here's a gravitational potential, and then all the photons try to go into the potential. But then if photons are collapsed, then this becomes high temperature, and the high temperature, there's a radiation pressure, right? Oh, it's radiation, it's too hot, right? So pulled, push back, this kind of oscillation is going to happen. And the oscillation, we know this relation, right? Oscillation frequency is sound speed divided lambda is going to give you oscillation frequency. That's basic physics. And then we can put from the sound speed. Sound speed we can theoretically calculate because we know the density and temperature of the universe. We know the density from how much variation is there, and we know the temperature from how much radiation and the size of the universe, and then it can be written like this. This theoretically calculated. And then, so I mentioned from the inflation that the density perturbation were scale invariant, right? We talk about the fractal universe. However, there are some preferred tones than others. Then entire universe acted as a resonance cavity with the sound of, with the size of sound horizon. So in this photon baryon fluid, you know that this kind of thing, right? So say you have beer bottle, and then you blow like woo, and then in some frequency it makes a sound, right? When the sound wave matches the size of the bottle, it makes a sound. Something like that happened in the entire universe. So let's say this is the size of the universe, entire universe, and when this oscillations wavelengths matches the size of the universe, there's a resonance, just like this beer bottle, and then it has first tone, second tone, third tone, fourth tone, this kind of tones. Okay. And then that's what we see here. So this is the CMB power spectrum. So this is a fluctuation power as a function of multiple moment L or angular size. So this is power spectrum, so it's in a Fourier space, showing how much fluctuation are there at a particular angular scale. Okay, if you remember, we did the spherical power spectrum maybe last week, right? Okay, well, simply speaking, so in these regions with larger power, these scales, there are more fluctuations. So here's a more fluctuation, less fluctuation, more fluctuation, less fluctuation, more fluctuation. And then these scales, something like a degree or smaller degree, maybe 0.2 degree, corresponds to these overtones that we saw there. Okay? We see it here, right? We saw that in some scales, some wavelengths, they are resonance, right? And then that's what we see in the power spectrum here. So in this case, in these three scales, here, resonance is happening. This is the, size of the universe divided by the wavelengths of the fluctuation. So this is why we have a fluctuation in cosmic microwave background. Okay? And then today, we're going to learn cosmological parameters from this. And then these acoustic peaks, these are the reasons we can do a precise precision cosmology. By measuring this precisely, we can precisely measure cosmological parameters such as omega lambda or omega matter, amount of dark energy or dark matter. So that's what we're going to learn today. So, I hope you can take away today that how we know amount of dark energy or dark matter from fluctuations of the cosmic microwave background. Okay, so that's the intro. So maybe I stop here and then maybe we go to one of your presentations. Okay? Either way is fine.
Just either side.
1, 2, 3 and go. Okay. 1, 2, 3. 1, 2, 3. Alright, okay.
You decide.
I go first.